Welcome back. In this little vignette, what we're going to do is describe what I mean by doing physics to it. I'm really excited about this one because it has to do with the philosophy of the entire course. And the idea is that we are faced with the world around us, inanimate and animate world, and we want to understand it. When I look out the window to my east, right here from my house, I can see the valley out towards Palm Springs, and we were observing this morning that the sun makes this very systematic voyage every year. It goes south and it goes north up to the mountains and goes south with quite a bit of regularity. But it really took thousands of years for people to actually get to the point where that was more than just a casual observation and where they had, let's call it, done physics to it. So the idea here is I just want to give you a flavor for that, first by giving you concrete examples from physics, and then I'll show how that's been parlayed into thinking about biological problems. So earlier, when we talked about Schrödinger and his book, What is Life? I argued that this notion of accounting for was really the essence of what he was after in his discussion of what is life. And so, just as a reminder, when we use the words accounting for in the context of spectral lines, what I had in mind was the idea that one would be able to identify first the wavelengths of those spectral lines, next, with a little more sophistication, the amplitudes or the brightness of those different lines, and then when we keep going, the splitting in those lines and in the presence, for example, of a magnetic field or an electric field, the Stark effect or the Zeeman effect, respectively, and so on and so forth. So accounting means that one can take a natural phenomenon. There may be some empirical insight, such as in this case the Balmer formula, such as in the case of springs, Hooke's law, such as in the case of thermodynamics, the ideal gas law. These are all phenomenological descriptions of what has been observed in the world. But then once those observations have been made, they've been codified in the form of some sort of phenomenological law, one would like to actually find the underpinnings for that law and use those insights to make predictions. So I wanted to just give a little bit of a gallery of examples that have meant something to me. So perhaps one of my favorite all-time ones is the measurement of the radius of the Earth by Eratosthenes. And the reason I like this one so much is that this was really my introduction to the idea that science is not about authorities, but rather about having a question and the investigator and the external world come into harmony through some experiments and some cleverness to try and get an answer to some question. So in this case, by looking at the shadow cast by the noonday sun on June 21st, summer solstice, and knowing the distance between two sites at which this shadow was measured, Eratosthenes was able to get a very accurate measurement of the radius of the Earth, way more accurate, I think, than I could do with a year's preparation and the absence of modern techniques such as GPS. From there, I want to move to the continued history of mechanics, and in particular talk about Galileo. And I think it's very important for us all to think about how it is that he was able to figure out concepts like S equals 1/2 gt squared, the law of free fall, in the absence really of a clock. It's something that we take for granted. But he, by basically changing the height of that platform that you see on the right, he was able to figure out how far the thing had fallen, and then he used various methods for clocks, like the flow of water through an orifice and so on. At any rate, this led to, again, if you like, originally a phenomenological law of projectile motion. It is not the result of F equals ma or some deeper insight. It's just basically an empirical statement about what he had observed. Next on the scene was Newton, and I think this figure in the upper right is one of the best figures in the history of science, because what it does is it unifies the insights of Galileo on projectile motion, which you see basically there's a mountain and you're shooting projectiles off this mountain, and you shoot them with sufficient velocity, and what will happen is that projectile, instead of having a parabolic path, which ends up colliding with the Earth, ends up turning into an elliptical orbit. And so here, I'm not going to go into the details right now. I might later if we have time, but I just want to point out in book 3 of the Principia, Newton basically says, well, let me figure out how far an apple falls in 1 second, and then let me figure out how far the moon falls in 1 second. or how far the moon falls in 1 minute. That's a little bit, there's a subtlety there that's kind of amusing, because a minute is 60 seconds, and 60 squared is 3,600, and the distance to the moon is 60 times the Earth radius. So there's a very interesting little coincidence there that Newton exploited. But never mind that. The main point is that he was able to basically infer that the law of universal gravitation was an inverse square law. And this is what, again, this is what it means to do physics to it. You know, you have a mundane observation. Everybody from the history of the world, probably all humans, have seen falling bodies. And all humans have seen things oscillating under the action, for example, of the wind, a tree, or whatever. But it's quite another thing to do physics to a problem, to basically insist that the measurements be made with increasing accuracy. And then in light of those measurements, that some sort of insight is garnered. And then once that insight is garnered, one tries to justify that insight, and so on. Another aspect from Newton's work that I want to give an example of, because I think that biology is crying out for this, is abstractions that in the end up being fundamental truths. So in the case of Newton, he was very intrigued by the fact that he could pretend that the moon and the Earth were points. In other words, point masses rather than extended objects. And he got to wondering about would there be a formal way of demonstrating, yes, a spherically symmetric mass will behave as though all of its mass is focused or concentrated at its center. And so why do I tell you this? Because this is, again, doing physics to it. What does that mean? It means that you're faced with some complicated mess. The idea being, if I have a spherical object and I drop a body, like if I drop an object right here in my office and I drop it, it's attracted to all points on the Earth with an inverse square, but that means that the points that are nearest to me attract it more strongly than those on the other side of the Earth. So how does all that conspire to give something which is effectively like the mass of the entire Earth is concentrated at its center? And using calculus, which he invented, Newton was able to prove that as a fundamental theorem. And I've already seen in my short career that there are many examples like that in biology, where at the end of the day, one can actually demonstrate something is a truth, even though at first cut it seems preposterous. And just to give you an example, one can prove that if you have a competitor ligand competing for an allosteric enzyme, one can actually integrate that out and pretend that there is no such competitor present, as long as the effective KD of the remaining substrate is an effective KD rather than the exact one that you would measure in some in vitro reaction. Moving forward sort of in the history of our physical understanding of the world around us, the inanimate part of that world, one of the things that happened after the success of mechanics was that people started to wonder whether other phenomena could be given a mechanical explanation. For example, heat and temperature. Even getting heat and temperature to be distinct concepts was not easy, but then people started building steam engines, and every steam engine was its own unique adventure until Sadi Carnot came along, and he realized that there were certain abstractions that could be made about those engines that were independent of the details of implementation of the hot and the cold source and so on. And so I just want to point that out also. So moving forward from the mechanical era to now trying to take stock of what's going on with electricity and magnetism, this is one of 2 pages from Maxwell's book that I think is one of the most impressive things that I've ever seen. So what's going on is shown in equation 9 and equation 10. What Maxwell has done is to write down an equation, a wave equation, for the motion of the electric field, the dynamics of the electric field. And what he notices in equation 10 is that there's a speed. In other words, when you write down a wave equation, the wave equation has 1 over a speed squared, generically. If you go examine wave equations, you'll see that that's the case. Whether it's a string or light or sound, the wave equation will have a 1 over a velocity squared. And so he recognized that this velocity looked like the square root of 2 very interesting quantities, which in modern parlance are epsilon 0, the electric permittivity of free space, and mu naught, which is the magnetic permittivity of free space. And what he did is he noted, well, heck, that means that the velocity of these waves is given by this very odd combination of something that has to do with static electric fields and magnetic fields from steady currents. And then he asks himself the question, well, how does this actually compare to what we know about the velocity of light? So here in the middle of this page, you see several different measurements of the speed of light in meters per second. And then on the right, you see what happens when he uses the known electric and magnetic units and computes a corresponding velocity. And he says, look, these are pretty similar. He says, it is manifest that the velocity of light and the ratio of the units are quantities of the same order of magnitude. Neither of them can be said to be determined as yet with such a degree of accuracy as to enable us to assert that the one is greater or less than the other. It is to be hoped that by further experiment, the relation between the magnitudes of the two quantities may be more accurately determined. In the meantime, our theory, which asserts that these two quantities are equal and assigns a physical reason for this equality, is certainly not contradicted by the comparison of these results, such as they are. This is incredibly profound. This is what it means to do physics to it. It took hundreds of years, but the bottom line is that starting, for example, with Rømer, who measured the speed of light by looking at Jupiter's moon's transit at different times during the Earth's orbit around the sun, to Gilbert's measurements with lodestone and magnets. It's a very long history of trying to come to terms with simple, elementary observations that anyone could make, just as anybody that lives in Pasadena, as they look out to the east, they can notice that over the course of the year, the sun is making an up and down journey, and that calls for physicsing. And that's really my point. And similarly, when we look at climbing plants, that calls for physicsing. And so although this is a biology course at Caltech, I feel no compunction to be sharing with you a very strong conviction that there's something to be gained by bringing the sensibilities of physics to the already deep and profound work of biologists. I think I'm going to pass on this. So now what I want to do is I want to just give a few comments on what it would mean to do physics in the context of biology. So one of the things that we'll do in this course is we will examine gene expression. And when I say examine, what I mean is from a quantitative point of view. We will think about the construction of genetic circuits in bacteria, in yeast, in Drosophila, in stem cells, with the objective of testing what we think we understand. And so what's shown on the right is predictions of the level of gene expression as a function of the number of repressors and the strength of repressor binding sites to DNA and so on. And these are all things that will work out, but my main point is that doing physics to it means that we actually can write down graphs. And those graphs are a statement of expectation about what will happen when a certain experiment or category of experiments are done. Another example that we will also touch on that I'm very excited about is that of Alistair. I heard it said, there's a very famed biologist who said he wouldn't even talk to physicists that were thinking about switching to biology unless they could define Alistair. Alistair is one of the most important ideas in biology, and the model of Alistair is, to my mind, the most important model there is in biology because it's got the farthest reach. So this refers to the fact that certain proteins specifically can exist in two different states, an inactive state and an active state. And the propensity to be in either the active or inactive state is tuned by the presence of a ligand. So the ligand in general will favor binding to either the inactive or the active state. That depends on the particular circumstance. And this kind of thinking can be used to think about chemotaxis, as shown in the left, can be used to think about quorum sensing, as shown in the middle, or about gene expression. And note in all of these cases that I'm presenting what's called a data collapse, which means that the natural variables of the problem, what the cell cares about. In other words, in the lab, we pipette things at certain concentrations, and we care about that because that's what we actually have to do when we go into the lab and put on our gloves and use our pipettes and we mix stuff. We're trying to actually get to a particular concentration of something or other. But that's not necessarily what the cell cares about. The cell might care about some combination of number of repressors, amount of inducers, strength of binding site, and so on. And altogether, that dictates a certain occupancy or a certain level of activity. And so it's the natural variable that really is the key point. We're certainly going to talk about diffusion as biology's null hypothesis for dynamics. And of course, the theory of diffusion has been around for centuries, really goes back in some ways to Fourier's original treatise on the theory of heat. But never mind. The bottom line is that the things that have been figured out about diffusion are quite relevant for all sorts of different problems, whether it's the behavior of bacteria in the presence of a chemoattractant, as shown in the lower right, or the existence of morphogens, as shown in the lower left, inside of embryos, to chemotaxis of human cells, etc. So that's an example of doing physics to it. Another example that I will be very excited about has to do with using elasticity to understand problems in morphogenesis. So this goes back to work from Mahadevan and Cliff Tabin at Harvard and their various postdocs and students. And the question that they were interested in was trying to figure out if they could understand the nature of the pattern of a folded gut. And when I say the pattern, what I mean is the wavelength of the pattern. In other words, there's an undulation. We want to know what's the wavelength, and also the amplitude of that undulation. And as we will see often, and really a deep concept, is these things are often dictated by a competition between two energies which have different desires. So on the one hand, you have the energy to stretch this mesenteric sheet. There's another energy associated with the bending of the gut tube, and those two energies are at odds with each other. And so what happens is that the system balances these two things in order to optimally satisfy an energy minimization condition. And out of that, one has a prediction for the wavelength and the amplitude of these undulations that we call gut folding. And so in these beautiful experiments, they looked not only at chicks, but I think they looked at quail, and I forgot what other, and they also even made sort of an analog rubber sheet associated with a rubber tube in order to test these ideas as well. Again, eye on the prize. Why are we talking about this? What am I babbling on about? I'm trying to motivate the idea that we've reached a moment where the quantitative data that's now being obtained in biology demands corresponding quantitative models. It's not enough to use words to describe graphs like those shown on the right. That falls short of what the data demands of us. And so doing physics to it means to have this interplay between theory and experiment and to try to get to the bottom of effects like those that I show you here. Another example that we will talk about that I'm also quite excited about is the pulsatile shortening or pulsatile elongation of cell-cell junctions. And this is something that's been observed, for example, in the context of morphogenesis in Drosophila by Thomas Lequi and his collaborators. And this beautiful work actually leads to a prediction about, if you like, an equation of motion for the length of this junction as a function of time and as a function of the density of myosin. And so what we'll do is we'll examine this theory and we'll work out for ourselves how the length of the junction goes as a function of the various parameters that show up in the theory. But this is what I mean when I say doing physics to it. Probably the final example that I'll use here, although not for sure not the final example of what will happen in the course, has to do with active flows, for example, here in the giant algae called Cara. So this is a very long single cell, cylindrical. It has this beautiful barbershop pole flow where in part of it the flow is upwards, part of it the flow is downwards. And we will show how we can use the equations of hydrodynamics to understand these flows. So the idea in a nutshell is that there are actin filaments and myosin motors, and the motion of those motors actually entrains fluid. The fluid which is entrained then is basically a boundary condition of what I show on the right as a flow with velocity v0. And we can use the Stokes equations to work out the profile. And even more interestingly, as done by Woodhouse and Goldstein, we can consider the coupling between the hydrodynamics of flows and the actual alignment of the filaments. In other words, this is a coupled problem of partial differential equations to explain the nature of the flows and the filament polarities associated with these beautiful and very fascinating cells. So this is just to give you a flavor for the kind of dynamics that emerges that you can read about in the paper of Woodhouse and Goldstein. So what's the summary statement? The summary statement is that the spirit of this course is, in some ways, if I'm being kind of harsh in my words, I would say that my take is that I really much prefer the mindset of physics for describing the natural world around us. but I currently much prefer the problems that have been considered by biologists to those that are currently really most exciting in the physics community. Of course, let's not forget, these are subjective opinions that I'm expressing, and I'm basically just trying to encourage you to join me in these enthusiasms. So with that, I will call it quits for this